Jerry. It's a pleasure to be here again with all the friends we have in this room. Today we're going to talk a little bit about how we approach solving problems for our customers in developing and building boards for embedded systems. We're going to cover a couple of topics, go through some challenges, some of the new challenges, and then look at some of the evolving technology in FPGAs, which is central to all of our product line. And then look at a new interface standard for data converters, which is kind of our bread and butter in putting these systems together. And then look at another new standard for FPGA interconnection of blocks. And then finally look at some new tools and how they're being used. So these are all of the challenges that everybody in this room who's supplying product to the industry is trying to solve and overcome. These are problems that continue to evolve. You don't solve it once. You keep solving it over and over again. And each time the solution could be a little bit different, but these problems are those that face us all. To try to meet these problems or challenges, you can get some help from new device technology. You can get some help to speed things up with faster interconnects, as we've seen. Evolving standards. You see it, the Vita is, of course, king there. And then FPGA standards. And then graphically oriented tools to design at a higher level, and also a high-level API for the software tools. So we're going to talk a little bit about all of these topics in a very short time. So it'll be kind of a high level with a few examples, and then finally I'll wrap it up with a product that kind of puts it all together. So if we take a look at some of the help that Xilinx has given us in terms of solving some of the problems in terms of function and speed and numbers of channels and sample rates, Xilinx has evolved through these families from the Xilinx 4 Series 4, 5, 6, 7, and instead of 8, they chose the name UltraScale. So it really should be 8, but they call it UltraScale. We'll just have to live with that. And this shows a dramatic increase in the number of logic cells with each successive family within a 42.5 or 40 millimeter square package. So you can see that this is all going up. At the same time, the geometry size is shrinking down to 20 nanometers now, where you get more resources in the same size. So that's kind of how they do it. If we take a look specifically at some of the metrics, just to show you the dramatic change in not just the logic cells, but also in the number of DSP slices. The latest Kintex UltraScale, and this is plotted on a relative scale of 0 to 100%, comparing the three families, the Virtex 6, Virtex 7, and the UltraScale Kintex. So on a relative scale, you can see some dramatic changes. We now have 5,520 DSP engines in a single FPGA. That's a tremendous amount of processing power. The speed of DDR4 SRAM is now 50% faster than the previous generation. The Virtex 7 supported DDR3 at 1600 megahertz. Now we're at 2400. The size of block RAM, a very important resource in the FPGA, is up significantly. And the number of configurable logic blocks, these are building block elements, is more than twice what it was in the previous generation. That's a tremendous increase. But at the same time, because of shrinking geometry and process change, what they've done is reduced the power. And so the relative I/O power, this is the power it takes to drive an I/O pin. You can see the largest here, the blue is the Virtex 6, is 100%. And down to the Kintex UltraScale, we're down about 56% of the Virtex 6. Similar savings in dynamic power. This is the switching power in the FPGA. And then the static power. This is the power that the FPGA consumes when it's not even working, but which, of course, causes heating and power supply requirements. So these dramatic changes, really dramatic changes, are helping us satisfy what our customers are looking for with all the demanding rates and so forth. We've had 3 different generations up to and including the Jade, which is our latest UltraScale product. using the Vertex 6 and Vertex 7. And these are just some of the numbers in terms of specific numerical representation of the resources. And the point that we're saying here is, if you're using XMC module, which is an industry, very, very popular industry standard that's used in just about every form factor, you can choose by more than a factor of 10 the number of resources and the horsepower that you might need for a particular function. So our customers can choose from a wide range of capabilities and still be able to move from one XMC to another without having to completely change their system. So it really helps to minimize life cycle support. The other thing that happens is the power and the cost are both down significantly from the previous generation parts, ranging from 30 to 50% in the cost per logic cell, and the power dissipation dropped by 20 to 40%. All good things that we all want. So, the other thing that good FPGA designers will do when they deliver a product to customers is they'll put in as many of the standard features that most customers will need. You would never want to give a customer a board that just has an FPGA on it and some A to D converters and connectors and say, here, you put it all together. So, I mean, that's one way of doing it, but this is completely opposite of our approach. So what we do is we put in all of the standard architecture that customers need in most applications for software radio, for radar, and so forth. So we have acquisition engines for like radar range gates, we have down converters, we have real-time power meters, we have time stamping, and then the DMA controllers help us move the data from our board into your system memory so that you can tell the board exactly when you want to capture the data, what bandwidth you want to capture, and where you want to put the data when it's captured. That's all part of our standard architecture, and it's the way that boards should be delivered to customers who need these functions. One of the challenges, now we're getting down into one of the fine points here, that we're seeing at this point is a transition in the interfaces from our high-speed data converters, A to Ds and D to As, moving from LVDS to a new standard. LVDS is really quite simple. In this case, a 12-bit A to D converter, you'd have 12 lines. You have one clock every sample, and 12 bits, 1 bit per line, comes out across that interface, and you just keep going, and it's extremely easy to use. So it's really, again, simple is good, and you change the clock rate to the A to D, the sample clock, the data rate changes. The FPGA takes it. It's very simple. The problem is, as we get faster and faster in data converters, as we get more channels, like multi-channel, dual-channel, quad-channel devices, the number of traces that you need on your printed circuit board really gets out of hand. So for example, a 12-bit 3.6 gigahertz A to D converter from Texas Instruments takes 4 sets of 12 lines, which is 48 LVDS pairs, or 96 wires on the printed circuit board to connect between itself and the FPGA. What that does is it consumes a lot of pins in the FPGA, and it takes a lot of board space. The aggregate rate we get here is about 5.4 gigabytes per second in this example, but it took a lot of wires to get that. So what's happening is the data converter interfaces are switching over to a new standard called JESD 204B, and it's a gigabit serial standard. It has been adopted by JESD, so it's widely used now. And what it does is it replaces the parallel LVDS lines with gigabit serial links. It's like we had parallel PCI move to PCI Express. It's a very similar kind of transition. Why? Because it's faster and there's fewer wires necessary. So it really is a complete protocol. You've got a transport layer, a link layer, and down to the PHY layer. So it's a very complex protocol to do it. You need channel encoding and so forth. The advantages are you have far fewer traces, although they have to be well controlled, matched for length and so forth. They can connect directly to the high-speed serial interface pins on all FPGAs, and they do support higher data rates. Now, here's an example of 1/2 of a new data converter from TI that we just put on a product last year that has a 3 gigahertz 14-bit A to D. It delivers its data over 4 pairs or 8 traces on the printed circuit board for about 5.25 gigabytes per second, almost the same as that previous converter that took 96 wires to do the same job. So we go from 96 wires to 8 wires. It's a big advantage. But there are some disadvantages. Each of the different modes, and there's a lot of different modes in these devices, different DDC modes or raw modes, have different framing of the data. And so the receiving device has to be adjustable to interpret those different frame patterns. The other thing is that the bit clock on the serial lines is locked to the sample clock of the A to D converter. So the bit clock in the receiver in the FPGA has to be reprogrammed in order to lock up to that new data converter driven bit serial rate between the A to D and the FPGA. That's very hard to do. And so the whole thing is that requires a lot of design on the board developer's part to make it so that these difficulties and complexities are completely abstracted away from the user. So it really it takes a lot of work. When we deliver this product to a customer, he doesn't even know how to spell JESD. He doesn't care. He just wants to get an A to D converter into his FPGA and then out. So it's a challenge, but it's the challenge that's moving forward that everybody has to face. Now, another standard that's helping us as FPGA developers is the AXI4 standard. How many of you have heard of AXI4? Okay. It's a new standard it's derived from ARM. It's a open standard. There's no licensing. The AXI4 specification is derived from the AMBA architecture, and it's being adopted by both Xilinx and Altera as the method for interconnecting IP blocks within their FPGAs for a lot of good reasons. And so what are some of the reasons? Well, it handles a lot of the housekeeping of connecting one block to another. It takes care of matching data widths and data rates and so forth, kind of automatically. And if you use the AXI4 guidelines for building your interfaces to IP blocks, then when you create your own blocks, it'll be compatible with this new standard and other blocks from other vendors. So you can plug in cores from third parties, from Xilinx, from Pentec, from other people, and really make it quite easy for you to design at a high level in a graphically oriented environment, as we'll see in the next few slides. A bus is simply, just a single wire on the block diagram. That represents a very complex collection of signals in the AXI4 definition. So this really improves productivity. Our engineers are using it, and they're saying that some of the things they're being more productive by a factor of 3 to 4 times. So it's really a nice new standard. So what we do is we deliver our IP, all the different blocks, the timestamping and the DDCs and so forth, as these AXI blocks, which all then, in a graphical representation, look like this. So each of these blocks shows up in the tool, the IP integrator tool from Vivado, as a high-level module where the heavy lines represent large buses that are connecting one block to another. And the nice thing about this is that if you click on these blocks, you immediately can go down to the inner VHDL code if you need to, or you can hyperlink over to all the documentation for that block. So you can find out exactly how the block works, what its inputs and outputs are, and how it behaves. So it really makes FPGA design a lot easier. So if you previously had designed with VHDL, just putting in lines of VHDL code, it isn't as friendly, let's put it that way, as it is now with the IP integrator tool. And we see, for example, these are different blocks in the tool, and this is a Pentec block, and this is a Xilinx block. So we developed our blocks for our new Jade architecture to be exactly the same style as the Xilinx blocks. And this is really kind of brand new for us, and I think it's going to be a major shift in the industry where everybody's going to start using AXI 4 as the way to build and integrate FPGA designs. We also have a support package. Together, these tools, the Navigator tools for the FPGA design and the board support package for the software design, C-callable high-level API that's used to control all of the IP blocks. There's a one-to-one relationship. So when a customer makes a change to one of the IP modules, he can easily go over to the software block that controls that module and make a corresponding change to the code in the software module in the API to reflect the changes that he's made in the block. Just as an example, this is an example of a Jade architecture board which uses 8. This can be a XMC module, it can be 3U, a 6U VPX, compact PCI. Because it's an XMC, it's extremely flexible. But it has 8 16-bit A to D converters that use the JESD 204B interface. So these JESD connections are all made for the customer. They're all installed in the board and ready to use without the customer having to worry about it. We're also taking advantage of the higher speed SDRAM, the DDR4 SDRAM from Xilinx. We're taking advantage of the Vita 66.4, which is an optical interface that we've been talking about earlier, to go to the backplane in VPX with 8 lanes of 10 gigabit per lane traffic going out to the backplane. That's about 8 gigabytes per second going out optical to the backplane. And of course, all of the other IP that we talked about before is all installed, including the digital down converters and so forth. So we're releasing this board at the show today, but we've kind of embraced all of the technology that we talked about just earlier into this product. So today what I did was I talked about some new device technology, specifically the Kintex UltraScale FPGA, faster interconnect technology, the JESD 204B interface, open hardware standards like the Vita 66.4 optical backplane connection, and then the open FPGA standards. What is that? It's the AXI 4 IP interconnects. Graphically oriented design tools. That's the Xilinx Vivado IP integrator. And then lastly, high-level API tools would be our Navigator tool suite. So all of these solutions are today's answer to all of the challenges. Next year, we'll probably have another whole new set of solutions, and that's what keeps this industry growing. That's what keeps everybody in business in this room. So, you know, that's the good news. It's always moving, always changing, and we're always trying to keep on top of it. I think that's it.